I'm Frank Moscatelli, a professor of physics here at New York University, and we want to talk about electrical power transmission. So you know that utility companies send electrical power from their sources to your home, and electrical power is equal to the product of current times voltage, and the unit is watts. You've heard of the unit watts. So being a product, you could transmit a lot of power with high current and modest voltage, or with modest current and very high voltage. Low amps, high volts, or low volts, high amps. Now your house runs at about 100 volts, 120 actually, but let's say 100 volts, and a typical home service is about 100 amps. So that means that each house uses about, on the average, 10 kilowatts. And therefore, for the entire community, a power company has got to transmit many, many megawatts from its source to the community. In fact, some of that is over a very long distance. So the question is, if your home uses about 100 volts, why doesn't the power company transmit all its power at 100 volts? If it did that, it would have to transmit that power over power transmission lines with many, many, many thousands, indeed possibly millions of amps. The situation of transmitting power with high amount of amps and low volts has a problem that we're going to show you. As you probably know, amps is the flow of electrons through a wire, somewhat analogous to water through a pipe. If you want to force so many electrons per second through a pipe, there can be all sorts of imperfections that cause resistance, and resistance, electrical resistance with current, generates heat. So over here, I have a demonstration where we're going to deliver power at a modest voltage. This thing puts out maybe a few tens of volts, but it's going to be many, many amps. And we're sending that current through a pencil here, which is like a transmission line. And the problem you'll see is when I force a lot of amps through the wire, because of the resistance of the wire, we generate heat. Generating a lot of heat, and in fact then failure of the wire. Okay, so high current, high amounts of amps causes wires to warm up and melt and break. And not only that, but that of course is power being lost. That power from the utility source never made it to the house. It's being wasted in the line. So, and that's something, of course, the power company doesn't want, because the power to your house is metered at your house. So what we're going to have to realize is that power companies want to use very small amounts of amps, but at extremely high voltages. And in fact, in order to transmit megawatts of power, which is the typical range of a community electric use, the voltages are going to have to be as high as hundreds of thousands, even 500,000 or up to 1,000,000 volts. So now we're going to demonstrate the transmission of electrical power, or simulate the transmission of electrical power at extremely high voltage, which would allow the company to have a modest amount of current flowing. The issue with transmitting at high voltage is, and you've probably seen, that the power lines that are called high tension lines have to be very high and very far from other surrounding structures. And that's because at extremely high voltages, the electric field near the wires can be so high that air molecules are ripped apart. The air molecules are ripped apart, and the electrons from the air molecules form a current in the air, and that's called an arc. That's called an arc over. Lightning is an arc over. And so the transmission of power, electrical power at high voltage, requires, isolation. It requires isolation of the high tension wires from any surrounding structure. We can demonstrate that to you here. We have ability to produce a voltage about as high as the high tension wires that transmit electricity. And this device is called a Tesla coil. And we're going to take some precautions. I do a lot of demonstrations in physics, and we're careful, but this one I am always afraid of. First of all, it makes a lot of noise, so we're going to go with earphones. And we're hoping that this point that will be at a very high voltage, many hundreds of thousands, as I said, possibly 500,000, we'll try and get it to arc over to this wand, and you can see an example of electrical arc. Hopefully it will arc over to this wand and not, say, to my head or any other part of my body or my videographer who's here. So we could die on this, but let's give it a try. You did test this. Oh, yeah. So, what you saw was very clear evidence of electrical arcing, again from this electrode, which was, many hundreds of thousands of volts high, and the arc jumped to that wand. What you didn't see or smell is, in fact, that at one point the camera cut out because, as I mentioned, the electric field is so strong that it disturbed the sensitive electronics of the video camera here. And what you would notice if you were in the room is that you would smell a distinctive odor from something called ozone. When I said the air molecules become ionized, they often form a molecule of oxygen, not O2, which we like and breathe, but O3. The chemistry on that is well known. So that's a demonstration. If you're transmitting electrical power at very high voltage, then the conduits, the high voltage, high tension wires, have to be very free of obstructions, and they can't get near them, and they can't be near any additional structure. I have nothing more to say.